Okay, hello everyone. This is the movie clip number 2 for week number 10. Um, in the previous movie clip, we have learned to derive the minority carrier diffusion equation. Okay, so since we are using the word minority carrier, so electron concentration in the p-type material, right? And the whole concentration in the n-type material. Those two 1 and 2, those are two equation is corresponding to the minority carrier diffusion equation. And for a given p-n junction, once hole has been injected into the n-type material, right, in this combination, the minority carrier diffusion equation of this can be applied. And in the previous movie clip, I have used the case in which hole has been injected into the n-type material, but equivalently, once a positive bias is applied onto the p side, the negatively charged particle electron would be injected into the p-type material. So this combination, electrons in the p-type material, take a look at the first line here, electron concentration in the p side. Okay, so how much excess electron, in other words, how much electron has been injected into this p-side material, delta n sub p has been varied over time, and that can be described by this second order derivative equation. Okay, so in this movie clip, we're gonna take a look at some specific example how the minority carriers are diffused throughout the silicon material. Then we're gonna have some hands-on solution and how the excess minority carrier concentration delta n sub p or delta p sub n can be described mathematically as a function of x along the x direction. Okay, so we're gonna do that in this movie clip. Okay, so before moving forward, let's take a look at some more examples for simplifications. Previously, we have assumed that the electric field is nothing, almost zero, in quasi-neutral regional p-n junction diode, and equilibrium electron or hole concentration is independent of x. In other words, p-type n-type material is uniformly doped, which is possible with the cutting-edge fabrication technology. And what else? Yeah, like low level injection, LLI. Low level injection is still dominant. In this slide, let's take care of a few more simplification. The very first one to be used in my lecture, steady state. So steady state means previously I mentioned that the difference between steady state and equilibrium, you can refer to my movie clip talking about the difference between steady state and equilibrium state. Okay, so please remember it. But let me briefly talk about the steady state versus equilibrium state. um, Sorry about that. Delta n versus time. So over time, delta n cannot be modified at all. So delta n, the value delta n itself has been well sustained over time. Then we can say that now delta n is in steady state. Okay, so here delta n in the p-type material, delta n sub p over around t is 0, which means in p-n junction diode, positive bias has been applied and electron is now injected into the p-type material. And this injected electron in p side, in p-type material, would affect significantly the minority carrier, I mean the n sub p, right? So this n sub p versus n sub p naught, those two values would be very different. And the difference is delta n sub p, right? So this delta n sub p is very dependent of how many electrons are injected into the p side, depending on the biasing. And here the question is, over time, this value delta np is not changed at all. Okay, in other words, or to keep delta np constant over time, this voltage, positive voltage applied onto the p side, should be constant. Then constant amount of electrons would be injected. So constant voltage means DC bias, right? So under DC bias, for a given voltage, say 0.2 volt or 0.5 volt, for a given DC bias, the total amount of injected electrons toward the p-side material is always constant. Then delta NP, if I take a first derivative of delta NP with respect to time, is always 0. Okay, so mathematically we can write down this. So if this steady state is available when you're doing your own analysis for p-n junction diode, even for MOSFET or MOS capacitor, whatever, then round delta NP over round T is 0. With that in mind, let's go back to the previous slide. Here, if the left-hand side is 0, what does it mean? If the left-hand side is 0, yes, steady state. Okay, so delta NP, excess electron concentration in p side, is 0 over time. The variation of delta NP to time is 0, which means steady state. Okay, so that's all for the first line. And second line is no diffusion current. Maybe you may have no chance to see that special case with no diffusion current. But if any, uh, no diffusion current is flown, then you can assume that the very first term in the magnetic carrier diffusion equation, this guy and that guy, okay? So this diffusion current part would be 0. And in some case, the authors has assumed that there is no recombination generation. Then, in the magnetic carrier diffusion equation, the recombination those two terms would be 0. Okay, and if there is no light, like a semiconductor chip, well packaged semiconductor chip doesn't have any light to be observed, so G sub L is almost 0, because semiconductor chip is well packaged. So maybe DRAM, NAND, CPU, AP, GPU, those chips are well packaged. But the CMOS image sensor, CIS, right? So CMOS image sensor, if you have a chance to purchase a professional digital camera, so if you take a look at the internal part of the body of your digital camera, you will see that the exposed semiconductor chip, which is a CIS image sensor, CMOS image sensor. Okay, so CMOS image sensor, CIS, has been widely used, in smartphone. So if you have a chance to, dismantle your smartphone, then you can see that just a bare, not packaged CMOS silicon chip uh, in the part of the camera of your smartphone. Okay, so the CMOS image sensors would uh, observe tons of photons or light. Then it can create electron hole pairs in the CMOS image sensor, and it can do some work. Okay. All right. So now let's move on to the example. Let's consider the special case. What case? Yeah, there we go. Constant minority carrier injection at x of 0. So here, this is a silicon bar, and it is an n-type silicon. Okay, so because of the externally applied light, many holes are created by this light. But here, the limit is the constraint is constantly holes are injected or holes are created at x of 0. In other words, at x of greater than 0, hole is not created by light. Only holes created at x of 0 by light, and the total amount of holes created is very constant by the light. Okay, that is a special assumption for this example problem. And the second assumption is a steady state. Well, once hole is created, the hole would be diffused toward the internal part of the N-type silicon material because of the hole concentration gradient. There are tons of holes and not too many holes available uh, in the internal part of the N silicon bar. So the second assumption is steady state. So the total number of created holes are very constant. So it's kind of a supply of hole. Okay. All right. So we can get this number. Uh, the meaning of the subscript n, right? N-type material. The hole concentration in the N-type material. Where? Yes, at x of 0, right? Here at the edge of the N-type silicon bar, the P sub n, but delta value. That means Pn minus Pn naught. So naught means equilibrium state. So without any light, this N-type silicon material has its own, hole concentration. If this silicon bar is doped as with a donor's concentration is 10 to the 18 per cubic centimeter, then N-type material at the molecular equilibrium is equal to Nd, that is 10 to the 18 per cubic centimeter. And using the mass action law, P and naught is equal to what? Yeah, N and naught Ni square, right? So 10 to the 18 and here 10 to the 10 per square, so that 10 to the 200 per cubic centimeter. So this number, Pn naught, especially at x of 0, is, well, in this specification, in this special case, suppose that the doping concentration is 10 to the 18, then that is 10 to the 2. Okay, but because of this light, this Pn at x of 0 is much, much higher than 10 to the 2. So this delta P sub n is not 0. Okay, but here we have assumed that steady state. So this value, delta P n x of 0, should be constant. Steady state means this difference should be well kept, okay, should be maintained. That means delta P sub n of x of 0 means constant. In other words, that constant means round delta P n naught divided by round T is 0. Okay, that is matched to the condition of steady state. Okay, so remember this, round delta Pn of x of 0, round T is equal to 0. Okay, so remember this. Then go back to the minority carrier diffusion equation again. Okay, remember this equation, and again here. Just a moment ago I said round Pn x of 0 round T is equal to 0. So this term on the left hand side is 0. Okay, so 0 is equal to what? This. Okay, but in the previous example, the light cannot be absorbed into the n-type silicon material. Okay, no light absorption at x of uh, positive section, so GL is still 0. So 0 is equal to what? This minus that. Remember that because I have copied and pasted where? Here. Okay, so please confirm it by yourself. Then now this minority carrier diffusion equation looks very simple. Yeah, very simple. Take a look at here. Those two, suppose that that is y. Then 0 is equal to dp minus 1 over tau p times y. So this equation, second order derivative equation, can be rearranged like that. Yeah, this type. C indicates a certain constant. Okay? So if we take a derivative of y 2 times, the shape of function is identical of its own. So from this second order equation, the general solution of this second order derivative equation is a exponential cx plus b exponential minus dx. This type. Only the exponential to the x is valid to satisfy the second order equation, second order derivative equation of this. Okay. All right. So we're gonna use it in the next slide. So go back to the original minority carrier diffusion equation here. Instead of y, I'm going to use a delta Pn as it is. So I'm going to rearrange the terms and here delta p sub n round square round x square is equal to what? Yeah, just move this guy and equal to ndp move. Okay, then we're gonna get this, and herein we're gonna define one new term, say L sub p. So L sub p means the whole diffusion length. So hole can diffuse uh, whole, once hole is created by electron by light, then it's going to be diffused toward the internal part of silicon bar, and how long these holes can be moved, can be diffused, then the diffusion length would be a good indicator, good metric, how long or how short the hole can be diffused. Okay, so in that sense, let's define the hole diffusion length as L sub p and square root dp times tau p. So here 1 over dp times tau p is defined as 1 over lp square. Okay, and now let's solve this equation. Let's solve this equation. Okay, again here. So how to solve it? Yeah, previously as I mentioned, this delta p sub n as a function of x should be the form of this, right? Otherwise, the general does the other, the other shape of solution cannot satisfy this second order derivative equation. So the general format or general solution to the second order derivative equation is this. Okay. The work left for us is to find out A, B. Okay. How to get A and B? Yes, we should have the boundary conditions. So in this specific example, what is a boundary condition? Yeah, boundary means edge, right? So x of 0 here and maybe here. maybe infinity. So those two boundaries would give us some hint to get the value of A and B. So now, uh, when at x of infinity, I mean the here, x of infinity, what is this value? Delta p sub n. So delta p sub n defined as Pn minus Pn naught. So Pn naught is always constant. What about this? P sub n. What does it mean? Yes, whole concentration in n-side material, but at x of infinity. So hole is created here, and it's going, say, 3 holes are created here, and it has moved, and 2 holes left because one electron would be recombined with electrons, and so it has been killed. And 2 electron is still traveling, and in the end, the 1 electron has left because this first electron has recombined with the electron, so it has been killed. And this electron would moving toward and toward into the silicon bar, and at x is infinity. Do you believe the hole is still there? No. At some point, the hole would be recombined with electrons. So at x of infinity, no holes left behind. But this hole means the newly created holes by light. So P sub n is approaching to the P sub n naught. So on the base, on the bottom of this silicon bar, or within this silicon bar, P n naught at equilibrium in n-type material, the whole concentration is kind of constant because the silicon bar is uniformly doped. But because of the light, the newly created holes are added up. So Pn naught plus alpha. So this alpha means the holes created by light. But at x of infinity, these additional holes would be recombined with electrons in the n-type silicon bar. So at x of infinity, the whole concentration at x of infinity would be equal to Pn naught. In other words, Pn x is infinity minus Pn naught is equal to Pn naught minus Pn naught is 0. And this number means delta P sub n x of infinity. So delta Pn x of infinity is what? 0. Okay, so there we go. So now let's plug in infinity into the x here, here, here. But this term should be 0. Then take a look at the two terms. Exponential plus infinity, that means this guy is huge number, infinity. But left hand side, it should be 0. That means this b, the coefficient b, should be 0. Otherwise, the 0 value on the left hand side cannot be appropriate. Therefore, b is 0. All right. But still, we have no idea on a. So let's do another job to look for the other boundary condition at x of 0 instead of x of infinity. So go back to the x of 0 here. What happened? Yeah, here delta p sub n x of 0 was kind of constant, right? So the author has provided us the number. This constant number is denoted as p sub n naught. So this is not variable. This is constant. Okay, delta p sub n naught means delta p sub n of x of 0. Okay. All right. So delta p sub n at x of 0 means a constant, but this constant is written as delta p sub n naught. Now let's plug in 0 value into the x here, here. Well, you don't need to do that because b is 0. Okay. Then now here delta p sub n x of 0 is delta p n naught. equal what? A times what? Exponential 0. 0 means 1. So the coefficient A is delta P n naught. There we go. Okay. Now, in the general solution, plug in A is delta Pn naught, B is 0. Then you're gonna get this solution for what? For this second order derivative equation. To better understand the meaning of the diffusion length here in L sub P, let's draw the plot delta Pn as a function of x versus what? Versus of x over Lp. Okay, so here x over Lp, this whole part is matched to the x-axis, and delta P sub n of x is matched to the y-axis. Okay, all right, then let's draw it. When this value is 1, that means delta Pn naught, I guess this A is typo, just to remove it. Yeah, delta Pn naught times 1, exponential minus 1. So exponential minus 1 is almost, I guess if I remember correct, 0.23, I guess. I guess 0.33, about 1 minus 67%. Okay, 0.33. So when x over Lp is 1 here, the value is delta Pn naught times 0.3. So this value is corresponding to delta Pn naught. So it's 0.33. So 1, 2, 3, 4, 5. So 20, 30. Yeah, about here. Yeah, there we go. 33%. This value. Okay. So what is this number 1 means? 1 means x over Lp. So x is Lp. Aha. So once hole is moved by what? By one diffusion length. Okay. If a hole is moved by one diffusion length, how many excess holes are removed or recombined with electrons? Yes, 67%. Where does this number come from? Yes, exponential 1. Okay. So it is like a RC network. You remember in linear circuit analysis, RC time constant stuff. So you remember this simple network RC. So this is V out, this is V in. So if V in is square pulse, then V out would follow the square first. But take a look at here. The steep, abrupt switching input signal has been applied, but this capacitor and resistor cannot abruptly follow this pulse, but it needs some time, right? So that time is characterized by RC time constant. So tau was R times C. Resistance times capacitance. The unit for RC is equivalent to the second, right? So by varying the R and C value, you can change this or that, or even this. Same mechanism can be happened here. How many newly created holes are survived as X is increasing? But here, X over Lp has been increased by 1, 2, 3, 4, da da da. Then the initial value, initial excess hole concentration was delta Pn naught, but X over Lp is 1, then only delta p sub n naught times exponential minus 1. And afterwards, x over LP is 2, then this value is delta p n naught times exponential minus 1 times exponential minus 1. At this point, let me write down here, delta p sub n times exponential minus 1 times exponential minus 1 times exponential minus 1, like that. Okay? In other words, the number of access holes are exponentially now decreasing. So within a few means a 3 or 5, just a 3 or 5 diffusion lengths, the access hole concentration has become almost zero. Okay, this is really important idea. In device physics, such as PN junction diode or MOSFET, for a given externally applied bias, how access carriers are decreased, you can say that it is following the exponence. The total number of access electrons or holes are decreasing exponentially. At an exponential manner, the total number of access holes and electrons are decreasing. Okay, so the basic idea and basic principle can be found from this second order derivative equation. Okay, this idea can be also found in RC network analysis. Okay, so I have explained some details minority carrier diffusion lengths, but herein, let me summarize it. Physically, LP or Ln means a hole in the n-type material, N means electron in p-type material. So minority carrier diffusion length represents, indicate what? Yes, average distance, not just that distance, average distance that minority carriers, not majority carriers, minority carriers can diffuse into a sea of majority carriers before being annihilated, before being killed. Okay, so before being recombined with majority carriers, how long on average the minority carriers can move? Okay, LP or LN, that is a main, indicators to explain how long the minority carriers can move. Okay, so for example, doping concentration is 10 to the 16 and lifetime minority carriers lifetime, in this case donor, right? So n-type material, so the minority carrier is the whole, so lifetime is 1 microsecond. What is diffusion length? Yes, dp times tau p. You know this tau p. What is this value? How to get it? Yes, I have already explained it. dp over lp is what? Kt over q. Einstein relation. So Kt over Q is constant, and Lp you would like to know. No, here. Mobility, sorry about that. Again, dP over mobility is constant according to the Einstein's relation. Then Kt over Q is at room temperature is 0.026. Okay, and you don't know the dP, but you know this mobility because you know the doping concentration. Do you remember this figure? Na plus Nd mobility. That is for electron, that is for hole. So once you know the total concentration of impurities, in this case, Na is not mentioned, so Na is say 0, then in this case 10 to the 16 say here, and now we are talking about the hole, so read out the value, maybe 400-ish, so just plug in 400 times 1 micro, then you're gonna get the value. So if I'm using calculator, then it said, so that is 400 and that is 0.06, so dp is square root 400 times 0.026 times 1 micro, and then it turned out that 30 micrometer. Okay, so you should get some hands-on number So doping concentration in N-type silicon is 10 to the 16, and the minority carrier lifetime is 1 microsecond, which is very usual and typical in silicon material. Then the diffusion length is 30 micron, a few tens of micrometer. Okay, so remember this number, and that would be good reference for you to design your own device in a company. So when you have a job in maybe Samsung Foundry or Samsung Memory Division or SK Hynix Memory, and your boss would ask you, hey, this area is doped with 10 to the 16, and let's use a typical lifetime of minority carrier. Then how long the minority carrier can diffuse in this specific region? Then you can simply say that, hey, maybe just a few tens of micrometer, 10 to the minus 5 meter scheme. Then your boss would be very happy. Okay. So remember that number as your own reference. All right. I guess let me stop here, and I'm going to come back soon to explain the concept of quasi-Fermi level. Okay, let me stop here and take a short break time by yourself.